Hello everyone, welcome to this new AtlanChim Pharma webinar about sodium chlorite and its use beyond Pinnick oxidation. Before I get started, I would like to remind you of a few points. Our last webinar in December was about reduction of azides to primary amines. Following our webinar on the radal on June 2023, and after discussions in particular with Chiara Coletto from Chematech, producer of this reagent here, we wrote this review to highlight the effectiveness of this amazing reducing agent through a selection of representative examples of different transformation. With Chiara and my colleague Arnaud Tessier from Sesame, we are very pleased that this review has just been accepted in OPRD. More than 10 years ago, we published a scientific letter on another methodology to oxidize the alcohols using TEMPO. You have here the chemical structure of TEMPO, and we will see later on this reagent. Like all the others, this scientific letter is available on open access on our website at this address just right here. Last month in May, we published a post on the LinkedIn in our fortnightly The Minute of Chemistry on the oxidative amidation with sodium chlorite, as presented in this slide. We will come back to this example later on. In fact, this surprising use of sodium chlorite gave us the idea of this webinar. So you have on this slide the summary of the different methodologies using sodium chlorite, which we'll discuss in this webinar through recent examples, mainly from medicinal chemistry and also from the total synthesis of natural products. Oops, okay. Sodium chlorite is a high effective bleaching agent and oxidizing disinfectant widely used for bleaching textiles and paper. It is also used to bleach sugar, fat, and wax. Sodium chlorite has found a number of other applications, which we will look at in this webinar. Sodium chlorite is a stable solid in absence of oxidizable organic material. However, sodium chloride can explode on impact, and mixtures with organic materials can be highly sensitive to heat, impact, or friction. So on the large scale, an 80% aqueous solution of sodium chlorite is used instead of the solid form. In organic synthesis, sodium chlorite is an inexpensive, green, and versatile reagent, which has been widely used for the oxidation of aldehydes to carboxylic acid under mild conditions, and this popular transformation is known as a Pinnick oxidation. In 1973, Lindgren was the first to apply sodium chlorite with scavengers such as sulfamic acid to convert vanillin to corresponding vanillic acid in a good yield at room temperature in water, as presented on this slide. He also used resorcinol as a scavenger with vanillin and obtained the same yield. Oops, oh, sorry. Oh, okay. A few years later, in 1980, in the course of the total synthesis of quasinoids, Krauss was the first to use 2-methyl-2-butene as a scavenger with an aqueous solution of sodium dihydrogen phosphate buffer at pH around 6.5 in a mixture of tiobutanol and water at room temperature. As you can see from this slide, this alpha-beta unsaturated aldehyde was efficiently oxidized to this carboxylic acid in a good yield on a scale of nearly 3 grams. In the 1981, Pinnick extended these reaction conditions to various alpha-beta unsaturated aldehydes without affecting the carbon-carbon double bond. Here on this slide, you have a representative example based on the experimental conditions established by Krauss a year earlier. Just a quick thought. Should we be talking about Pinnick oxidation or cross oxidation or even Lindgren-Krauss oxidation? In any case, the reaction mechanism of Pinnick oxidation is still not fully understood, although the following proposal here is acceptable. It has been proposed that the reaction mechanism begins with a protonation of the aldehyde by chlorous acid here, formed in situ from sodium chlorite under acidic conditions, to give this first intermediate, followed by an attack of a chloride ion on the carbonyl group to form this chlorite hydroxyallyl intermediate, which undergoes pericyclic fragmentation to release the carboxylic acid and hypochlorous acid as a byproduct. It has been found that hypochlorous acid here can cause undesirable side reactions, such as epoxidation of the electron-rich carbon-carbon double bonds. It should be also pointed out that the hypochlorous acid here destroyed sodium chlorite, leading to the formation of chlorine oxide, a problematic gas on large scale, as we will see in some examples. Thus, hypochlorous acid scavengers, such as 2-methyl-2-butene, resorcinol, sulfamic acid, and also hydrogen peroxide, are added to increase the efficiency of this oxidation process. In a typical procedure, the aldehyde is dissolved in tiobutanol, often in a combination with another solvent, such as THF or water, along with a large excess of scavenger, followed by the dropwise addition of the aqueous solution of sodium dihydrogen phosphate, and then hypochlorite, sodium hypochlorite in aqueous solution at room temperature. Important points to consider: to ensure a constant pH value of around 6.5, it is recommended to use several equivalents of sodium dihydrogen phosphate. Due to the instability of sodium chlorite in acidic medium, in the presence of metal salts, the use of a steel needle for the addition of the oxidant in water should be avoided and replaced by a Pasteur pipette, for example. Oxidation of Pinnick has many advantages. Stereocenters at the alpha position of aldehydes are not affected. Functional group tolerance is excellent. For example, hydroxy groups do not need to be protected. Sterically indred aldehyde can be oxidized, and also the reagents used for this oxidation are not expensive. In the total synthesis of this chromanol with antibacterial and antifungal activity isolated from this filamentous fungus here, this aldehyde was oxidized to the corresponding carboxylic acid in excellent yield on a multi-gram scale by a classical Pinnick oxidation. No epoxidation of the electron-rich carbon-carbon double bonds was observed. In the context of the preparation of potent non-nucleoside inhibitors of HIV-1 reverse transcriptase, this substituted imidazole carboxylic acid containing here an azide function was prepared by a classical Pinnick oxidation from this aldehyde in excellent yield on 7-gram scale. No comment was given by the authors concerning the very large excess of 2-methyl-2-butene used as a scavenger in this case. In the Pinnick oxidation, hydrogen peroxide here can be used as hypochlorous acid scavenger, resulting in the formation of oxygen gas. This oxidation of aldehydes to carboxylic acids with sodium chlorite using hydrogen peroxide as a scavenger is known as Dalcanal oxidation, and you have here the reference of this methodology. These conditions were applied to the oxidation of this highly elaborated aldehyde, 1.4 equivalent of sodium chlorite and 1 equivalent of hydrogen peroxide were used. The carboxylic acid was isolated in an excellent yield on a scale of nearly 3 grams. DMSO here has proved to be an effective scavenger of hypochlorous acid when used as a solvent. Then DMSO is oxidized to a dimethyl sulfone. However, the high boiling point of the solvent is a problem. So it was found that using a stoichiometric amount of DMSO was sufficiently effective in trapping the hypochlorous acid formed during the oxidation reaction. Also, dimethyl sulfone byproduct here of the oxidation was removed in the aqueous extractions during workup. As presented in this recent large-scale example, 1.5 equivalent of sodium chlorite and DMSO as scavenger were used to oxidize this aldehyde. The desired carboxylic acid here was isolated in a 68% yield on almost 300 kilogram scale. Relatively a few good general methods exist for the oxidation of primary alcohols to carboxylic acids. So in 1999, Zhao from Pfizer developed a tempo-catalyzed oxidation of primary alcohols to the corresponding carboxylic acids using a sodium chlorite as a stoichiometric oxidant. This example here shows a typical procedure. This primary alcohol was treated with two equivalents of sodium chlorite in the presence of catalytic amines of sodium hypochlorite and TEMPO in a mixture of an aqueous solution of dihydrogen phosphate buffered to pH 6.5 and acetonitrile. After 2 hours at 35 degrees, the desired carboxylic acid here was isolated in a 95% yield on 10 gram scale. It is important to point out that sodium chlorite solution and bleach should not be mixed prior to the addition, since this mixture appears to be unstable. Sodium chloride solution and diluted bleach are added separately, slowly at the same time. Another point, when sodium chloride was used alone as an oxidant, the oxidation reaction appeared to be very slow. The remarkable acceleration of the oxidation with a catalytic amount of sodium hypochlorite can be explained by the catalytic cycle proposed in this slide. The catalytic amount of sodium hypochlorite oxidizes the TEMPO radical to the N-oxoammonium ion A, which in turn rapidly oxidizes the primary alcohol here to aldehyde following this intermediate B and gives hydroxylamine C. The aldehyde here is then oxidized by sodium chlorite to the carboxylic acid, and sodium hypochlorite is regenerated. Hydroxylamine C can be then directly oxidized to the N-oxoammonium ion A by sodium hypochlorite formed in the previous oxidation step. Although the exact mechanism of TEMPO-catalyzed oxidation of alcohols is still unclear, previous work has shown that N-oxoammonium ion A and hydroxylamine C are involved. As we have just seen, sodium chlorite can readily oxidize aldehydes to the carboxylic acid without the assistance of TEMPO. The long induction period of the reaction without a catalytic amount of hypochlorite is probably due to the relative slow oxidation of TEMPO radical by sodium chlorite itself. Nevertheless, once the reaction is initiated, it becomes self-sustaining as sodium hypochlorite is continuously regenerated, which is consistent with the catalytic cycle described on this slide. This procedure is not applicable to allylic alcohols and substrates with electron-rich aromatic groups, as well as compounds containing a furan, as we will see in the last section of this webinar. One of the major side products in the oxidation with substrates with electron-rich aromatic groups have been identified as chlorinated compounds, as presented in this example. This side product is formed by electrophilic aromatic substitution and an increase in the quantity of sodium hypochlorite increases the proportion of chlorinated compound. In the large-scale preparation of this drug candidate for treating diabetes from L-xylose, oxidation of the primary alcohol of this intermediate to carboxylic acid was carried out with sodium chlorite and catalytic amounts of tempo and sodium hypochlorite in phosphate buffered aqueous acetonitrile at pH around 5. As mentioned before, both aqueous solution of sodium chlorite and diluted sodium hypochlorite had to be added separately at the same time, dropwise to the reaction mixture. In this case, the desired carboxylic acid was isolated as a crystalline morpholine salt in 95% yield on a scale of nearly 400 kilograms. It should be pointed out that the secondary alcohol here was unaffected by this oxidation reaction. In this large-scale oxidation, the reactor headspace was flashed with a gentle stream of nitrogen to prevent chlorine or an chlorine dioxide from reaching high concentrations. In the enantioselective synthesis of this potent anti-HIV nucleoside, this alcohol here was oxidized to the corresponding carboxylic acid using a 1-pot sodium hypochlorite tempo Pinnick oxidation. The authors did not comment on the use of a large excess of sodium hypochlorite. In the kilogram scale synthesis of this potent anti-tumor agent, the typical 1-pot sodium chloride tempo Pinnick conditions were applied to this primary alcohol derivative to provide the corresponding acid in a good yield on multi-kilogram scale. In this last example, this chiral primary alcohol here, containing a phosphonate moiety, is oxidized under typical 1-pot sodium hypochlorite tempo Pinnick conditions. A solution of diluted sodium hypochlorite of this household bleach was used in this reaction. Allylic and benzylic oxidations are an important synthetic transformation due to their wide variety of applications in the synthesis of pharmaceuticals as well as fine chemicals to get the corresponding enone and benzoyl derivatives respectively. Traditionally, chromium-6-based reagents such as ones presented here on this slide are used. However, the use of large excess quantities of reagents in most of these procedures, along with the difficult workup and the toxic chromium residues, makes such a procedure inconvenient on a large scale. Other classical stoichiometric oxidative processes involved the use of manganese dioxide, potassium permanganate, or selenium dioxide. A variety of catalytic methods for allylic and benzylic oxidations have been reported using hydrogen peroxide as oxidant. Salvador has described various allylic and benzylic oxidation to the corresponding enone or benzoyl derivatives in good yields using sodium chlorite associated with N-hydroxyphthalimide as a catalyst. These oxidation reactions were performed under mild transition metal-free conditions. For a mechanistic study of this transformation here, these two radical species are involved, And for this study, just see this recent reference just right here. For example, in the total synthesis of this lenostan type triterpene derivative here, a potent inhibitor of DNA polymerases alpha and beta, allylic oxidation at the C7 position here by treatment with sodium chlorite and N-hydroxyphthalamide at 50 degrees afforded the desired anion here in 44% yield. In the synthetic development and scale-up of a complex parazole fragment here of lenacapavir, a drug recently approved for long-acting treatment of HIV, CH oxidation using sodium chlorite and N-hydroxyphthalamide conditions was used to prepare this racemic ketone intermediate here on 300-gram scale as presented in this slide. The desired ketone was isolated in 95% yield. However, an alternative approach to this scaffold was developed due to the detection of chlorine dioxide in the reactor on large scale, despite the precautions taken, in particular the use of nitrogen stream. In this last example, sodium chloride oxidation of this hydroazolene sesquiterpene here gave this corresponding anion in 89% yield on almost 3-gram scale. We now turn our attention to the oxidation of amine to amide under Pinnick oxidation conditions. In the course of their research into alkaloid synthesis, Tomioka and his group have discovered that oxidation under Pinnick conditions is applicable to amines to provide the corresponding amides in good to high yields. They demonstrated the generality and the functional group tolerance of this oxidation protocol on various substrates. This slide shows a representative example with here typical conditions which are the same as those used in the Pinnick oxidation of aldehyde. Concerning the mechanism of this transformation, the amine nitrogen here was protonated by the acid, and the chloride ion attacks the amine carbon, which is then oxidized to the amide, 2,3,2-methyl-2-butene in this case, acts as a scavenger of hypochlorous acid, as we saw in Pinnick oxidation of aldehydes. The experimental conditions for this amine oxidation to amide are very mild, permitting it to be used at the final stage of the synthesis of highly functionalized substrates. For example, in the total synthesis of this isolated natural product from a marine source, Pinnick oxidation conditions here were applied to this amine to provide this lactam in a 58% yield. As the authors point out, this transformation here is robust and has overall reduced the length of the reaction sequence to prepare this key intermediate. In this last example, concerning the total synthesis of this tri-halogenated indole alkaloid, this amine here was oxidized under classical Pinnick conditions to provide the desired lactam in excellent yield. Sodium chlorite was also found to be a useful oxidant in coupling an aldehyde and an amine to form an amide bond. Tan here reported a one-pot reaction using Pinnick conditions to couple an aldehyde and an amine to give an amide. This group investigated this amidation between 4-chlorobenzaldehyde and N-butylamine, and the optimum conditions for the reaction are shown on this slide and are identical to those used in the Pinnick oxidation of aldehydes. Expect for the solvent toluene instead of terbutanol. As you can see here, the desired amide is obtained in good yield, and only 1.5 equivalent of amine was used. Concerning the mechanism of this transformation, it has been proposed that the aldehyde and amine first undergo a condensation reaction to form an amine. The amine nitrogen was next protonated by the acid, and the chlorite ion attacks the amine carbon here, which then oxidizes to the amide. 2,3-methyl 2-butene acts as a scavenger of hypochlorous acid. As presented in one of our last minutes of chemistry on the LinkedIn. Oops, it's dropped, sorry. So as presented in one of our last minutes of chemistry on the LinkedIn, in the final stage of the total synthesis of this complex natural product, this oxidative amidation was used to prepare this amide from this aldehyde and this aliphatic amine under standard conditions. The desired amide was obtained in 82% yield on a 100 milligram scale. To conclude this section, we have here on this slide an example of oxidative amidation under Pinnick conditions in toluene with an aromatic aldehyde, and the desired amide is obtained in good yield on a gram scale. It should be pointed out that the two-step sequence, Pinnick oxidation of this aldehyde to the corresponding carboxylic acid, followed by peptide coupling with a benzylamine here, provided the desired amide in less than 50% yield. Another application for sodium chlorite is a direct preparation of 2,3-epoxy amides. In 2012, these authors published an original and direct method to prepare 2,3-epoxy amides from tertiary allylamines using sodium chlorite via a tandem CH allylic oxidation, double bond epoxidation. A rational reaction course could be presented as the following. First, CH oxidation of the allylamine by sodium chlorite to the unsaturated allyl amide B via the formation of intermediate A, which might be initiated by chlorite radical here. From intermediate A, elimination of hypochlorite ion provides B. It should be pointed out that the first step involving chlorite radical is not clearly understood. Second, Michael type addition on the activated double bond of B here by hypochlorite ion formed in the previous step gives C here. Then intramolecular cyclization with elimination of chloride provides the 2,3-epoxy amide. Following this mechanism here, this oxidation reaction does not require the use of a scavenger because most of the hypochlorite ion here formed in this reaction, which is normally considered as an unwanted byproduct in Pinnick oxidation reactions, is consumed during the epoxidation reaction at this stage. This elegant methodology was successfully applied to the synthesis of a potent non-racemic inhibitor of glycolipid biosynthesis. As presented in this slide, treatment of this intermediate with this N-allyl moiety here in red with 6.3 equivalents of sodium chlorite and 10 equivalents of sodium dihydrogen phosphate in a mixture of THF, water, and terbutanol, THF, and water at room temperature overnight gave the desired intermediate in a 80% yield in a 10-gram scale as a mixture of diastereoisomers. It should be pointed out that under these conditions, the alcohol function here remained intact. In the last step of a total synthesis of this monoterpene indole alkaloid, initial attempts to access this target molecule via allylic oxidation and then alkene epoxidation of this intermediate resulted in the failure. Fortunately, treatment of this intermediate with sodium chlorite installed the amide and epoxide moieties in one step, giving this natural oxygenated indole alkaloid in good yield. To conclude this webinar, we are going to talk about oxidation of furan ring using sodium chlorite. Formation of 4-oxo-2-alkenoic acids from substituted furans has been reported with various oxidizing agents such as bromine, PCC followed by Jones reagent, or nitration followed by acidic oxidation. However, these methods suffer from prolonged reaction time, strong acidic conditions, low yield, and/or contamination with chromium salts. In 2005, Salomon described an efficient oxidation of electron-rich furan intermediates with sodium chlorite in a mixture of terbutanol and water with a pH 3.5 phosphate buffered at room temperature. And in this example, the gamma-hydroxybutyronide intermediate here was isolated in excellent yield. Treatment of this later intermediate with a catalytic amount of pyridine in a mixture of THF, acetone, and water afforded the E4-oxo-2-alkenoic acid here in excellent yield. In fact, in 2002, Cleve discovered this oxidation of furan ring as an unexpected side reaction in model studies on the synthesis of highly oxygenated complex compounds. This furan ring oxidation was applied in the total synthesis of this metabolite produced by this fungus, Xylaria longiana here. Oxidation of this 2,3-disubstituted furan intermediate with sodium chlorite gave this gamma hydroxybutyronide in 88% yield in 200 milligram scale. Although no detailed mechanistic studies have been carried out, it may be suggested that 2+4 cycloaddition between the furan ring and in situ generated chlorous acid here could provide this intermediate. The latter intermediate underwent rapid ring opening with liberation of hypochlorous acid to give this unsaturated keto aldehyde. Oxidation of the aldehyde here to the carboxylic acid with sodium chlorite provided this later intermediate. Via the formation of this carbonyl hydride, this intermediate was converted to the corresponding gamma hydroxybutyronide. In the total synthesis of this oxygenated polycyclic framework derived from membranes, treatment of this furanobutyronide-based microcycle with sodium chlorite under buffered conditions afforded the Z-diketone moiety in excellent yield. In the enantioselective total synthesis of this natural meroterpenoid, sodium chloride furan ring oxidation of this intermediate here delivered the desired gamma hydroxybutyronide in 65% yield. To end this section, in the first step of the total synthesis of this enoliter spiroacetol natural product, this furan derivative was efficiently oxidized according to the classical sodium chlorite oxidation procedure to give this gamma hydroxybutyrolide in 98% yield on a scale of about 2 grams. Next, pyridine catalyzed ring opening of the gamma hydroxybutyronide first from the Z-keto acid, which was isomerized to the E-isomer, and the desired adduct was isolated in 95% yield on almost 5 gram scale. To conclude, I hope this webinar has convinced you of the value of sodium chlorite, not only for Pinnick oxidation, but also for other transformations, as we saw together this afternoon. In more than 21 years of chemistry for our customers and more than 2,200 contracts completed covering a large type of chemistry, we have used at one time or another Pinnick oxidation, and also very recently this oxidative amidation with success. Since 2004, we also ensure an important scientific watch with our scientific letters, our webinars, and with a minute of chemistry on the LinkedIn. We have a strong expertise in the synthesis of label products, more than 350 compounds prepared. We have also a strong expertise in the isolation and synthesis of API impurities. So to contact us, you have here the email and a phone number of Aurélie, our sales manager. thank you for your attention. I would like also to thank my colleagues from AtlanChim Pharma for the discussions during the preparation of this webinar and Aurélie for the organization. I would like also to thank Laurence Arzel for her careful reading and her relevant remarks on the first version of this webinar. I think now it's open to discussions and questions, and thank you again for your attention. Okay, first question. Okay, for this question, the answer is yes. And if you check the paper of Tan from 2012, and the reference was in this webinar, it is mentioned that anilines have also proved to be an excellent coupling partner, giving the corresponding amides with excellent yield. Okay, I think it's very important to have a buffer because it's known that if you run the reactions at in the acidic media, you are going to form um, some chlorine dioxide, and sometimes the concentration of this gas could be really important. And that was described, I think, long times ago in the 60s by Barton, who used the, the sodium dichlorite as an oxidizing agent. And I think it's always better to be at buffer between, I would say, between 3 and 5, 6, something like that. But I think it could be important. Anyway, you know, in the very strong acidic media, I don't think it's good. For example, at pH 1 or 1.5. Yeah, that it's an important point. The epoxidation of olefins using sodium chlorite as an oxidant, and of course without catalyst, was described, I think, in 2005. And in this case, they used a very large excess of sodium chlorite. I think it was at least 10 equivalents. It was in acetonitrile at 50, 60 degrees. And it's, it, it does not appear to be very effective, and only works well with substrates such as steel bean and derivatives. Uh, I don't know exactly the price uh, on large scale concerning the sodium hypochlorite. It's a sodium hypochlorite or sodium chlorite? Because I don't think sodium hypochlorite at 80% in water is so safe. I don't know, but if it's sodium chlorite in 80% in water, I don't know the price, but what I know is sodium chlorite is produced in very large scale. I think it's the worldwide production of sodium chlorite is around several thousand tons per year, you know, and it's a very inexpensive compound. Okay. I wonder if you can use the reagent employed in the allylic. I don't know. It will be it's a good point. I don't know exactly if it's possible to use that as a tempo, but I don't think so because tempo is very important. You know, it's the tempo itself, of course, but it's oxoammonium intermediate, which is a key intermediate in the oxidation. You know. And I don't think it will be possible with the reagent we saw in the allylic and benzylic oxidation. Okay, thanks again for joining us this afternoon for this webinar. Okay, if you have any questions or comments, please don't hesitate to contact me. You have my email address. And enjoy your summer break, and bye bye.